Hey everyone, let's learn how to tackle this educator problem, BST equals AVL. So this problem gives us a binary search tree and asks us to evaluate if it's also a valid AVL tree. And the way that we evaluate this is we basically check the balance factor of each node, which is the height of one subtree minus the other. And if we find a node where the balance factor, the absolute value, is greater or equal to 2, we know that in that subtree, so say this 5 here, this subtree has a height of 1, 2, 3, 4, whereas this subtree has a height of 1, which means that the absolute value of the balance factor for this 5 is going to be 1 minus 4, or 3. So we know that this tree is imbalanced because its balance factor is too high or too low. For an AVL tree, we always want the balance factors to be either 0, 1, or -1. And since we see that this 5 has a balance factor of -3, we know it's not an AVL tree, and we return false. So let's talk about the intuition for how we actually want to transform. Let me zoom in so it's easier to draw here on this little example that's provided. Didn't help too much, but so one thing that we should realize is that to calculate the balance factor, we need the nodes, or we need rather the heights of every single node. And that just represents the heights. So for example, this node would have a height of 1, this a height of 2, a height of 3, a height of 4. And that allows us to calculate the balance factor, right? We can't calculate the balance factor without knowing the height of our two subtrees. And sure that there's many ways to kind of store the height. For the project, we actually recommend that you store the height inside of, sorry about this, inside of your nodes so that you can access it extremely quickly, right? You can just have it stored, say, in this 9 and this 16. So if you're at the 15, you can say, all right, get the height of 9, get the height of 16, calculate the balance factor. Pretty easy that way. Here, that isn't the case. But we still want to calculate the balance factor at every single node to determine if the BST is an AVL tree. Now, what we could do is, for every single node, look at the left subtree and the right subtree and say, calculate the height, which is a recursive procedure. But that would be inefficient, right? If we want to calculate this balance factor, we would say, okay, calculate the height of this, and that would require us to look through all of these nodes. And then we would come here to the 15 and we say, okay, calculate this balance factor, which requires us to look through these nodes again. Then we would calculate this one, requires us, and you can just see it's a lot of repeated computation. It's going to be pretty efficient. So instead, let's think about what the height function will actually do. So let's first start with a base case, right? Because we want to write this recursively, so we always think of the base cases first. So we know that a leaf node like this has a height of 1. So that's a reasonable base case to start at. Something that's a little bit easier, though, is to actually just have our height function return 0 when it's past a null pointer. So essentially, if we're at the 16 and we recursively call a height on its right child, we're passing in a null pointer to that height function. And when we do that, we know that this has a height of 0. And when the 16 calls height on both of its children, with both of its null pointers, it gets 0 back for the height of both of them. So if we do the height calculation formula of 1 plus the max height of either subtree, 16 will actually be assigned a height of 1. So that's correct. So let's start with that. If we're passed in a null pointer, we return a height of 0, because we effectively know if it's no node, it has a height of 0. Now, I mentioned a general height formula. Well, let's think about that. So let's say that in this case, we have a height of 3 for this 9 here, and a height of 1 here for the 16. Now, the 15 will have a height of 4. How do we know that? Well, it's always based on the larger subtree plus the extra edge we need to get to that subtree, right? So this 1 is essentially overshadowed by this subtree of height 3. So what we just do is we just, otherwise we return 1 plus the max height of the two subtrees. So height of the left and then height of the right. And so that's how we can implement the height functionality recursively. If we're fed in a null pointer, we return 0. And this means that root nodes, when they add 1 to the max of their subtrees, will have a height of 1. And this will continue upwards. This will get a height of 2. So we'll get a height of 3. This will get a height of 1. And then this will maximize across the 2. And remember, this is also treating this effectively as a 0. So it's always going to pick this 1 over it. This is going to treat this as a 0. It's going to pick the 2 plus 1 to get 3. Here it's going to take the 3 plus 1 to get 4. This has 2 zeros, so it's going to add 1 to 0 to get 1. And then this one will maximize, grab the 4, add 1 to get a height of 5. So nice. We're calculating the heights of each node. Now, we already have a recursive procedure that takes the height or calculates the height of each node. What if we calculated the balance factor? So this already accesses every single node, right? What if we then simultaneously calculated the balance factor? Because remember, in order to get the height of a node, we need the height of its two subtrees. But if we have the height of its two subtrees, we can use those two heights to calculate the balance factor of the node we're currently finding the height of. So this is something that we can kind of do these two operations in parallel. If we ever calculate a balance factor and it's greater or it's outside of that -1 to 1 threshold, we know that the tree isn't an AVL tree. And we can have our function return false as overall. If we don't see any node that exhibits that property, we can have the function return true. So let's return to a normal scale here. Let's start by just implementing the height functionality. So calculating the height. Let's make a helper function for this, because if we're calculating the height, we want to return it, which will be an int. So I'll call this check height, because we plan to not only get the height, but also to check the balance factor of the node we're getting the height from. So of course, we'll pass a root node. That's the node that we're calculating the height for. So like I said, this will be recursive, so let's do our base case first. So we'll check if the root node is null pointer. We can do that with this syntax here, checking if the root exists. And if it doesn't exist, then we'll just return 0, effectively indicating that the root has a height of 0. This means that any leaf nodes, when they call check height on their two null pointer children, they'll get zeros back from those, and they'll assign themselves a height of 1 in this else clause. What does this else clause do? Well, this will return 1 plus the maximum of the height of the root's left subtree and the height of the root's right subtree. So remember that this function will always return the height, right? If the root doesn't exist, it just returns a 0, which means that generally, if we want to calculate the height, we'll just take the heights of the two subtrees, maximize across them, again, like this 3 and this 1, we pick the 3, and then add 1 to represent the edge we take to get to that subtree. So this is all we actually need to write the height function. But remember how I said this is already looking through all the nodes, because it, again, it's starting at the root. We can call here, we can call it like so, check height. This is already looking through all the nodes. It will start at this root, and then this will recursively call it on every left and right node. So this will be called here, and then it'll be called here, and then this one will also call it here and here, so on and so forth. So we might as well, in this function, see if we can check the balance factors as well. And the way that we do that, we're already getting the heights. So remember, this function will return the height. We're already getting the heights of the left and right subtrees. So let's actually store those. So int left height equals this call to the root's left subtree. And then we'll store a right height equals check height Right. So we have the two heights. And remember, when we check the balance factor, the absolute value has to be, or the balance factor has to be outside the range -1 to 1 to make it not an AVL tree. An AVL tree will always have within this range. And so what we can do is, obviously, we want to subtract the heights and check if it's in that range. And what we can actually do is we can take left height minus right height and take the absolute value of this. So taking the absolute value will tell us the overall difference between the heights, because that's ultimately the point of what we're doing here. If the heights are just 1 apart or 0 apart, then we're fine. But if the absolute value, the difference between the two heights, is greater than or equal to 2, we know that the tree is too imbalanced to be an AVL tree. And therefore, this tells us that the tree overall is not an AVL tree. Now, how can we actually do this? Now, the easiest way to do this is frankly just to use a global variable. Maybe this is not, you might not see this as super proper, but is AVL. I frankly think this is a good example of when you can use a variable like this. We're going to assume that at first it is an AVL tree. And if we ever encounter a node with a balance factor greater than or equal to 2, or a difference in heights of subtrees greater than or equal to 2, we will set it to false. Because here we want this to be set to false. We want this variable to be set to false if any of the check height functions on any of the nodes encounter a imbalance that's too great. And so this is why we'll use a global variable here. There's some ways to alleviate this by making other functions that return different values, or just to straight up store heights in the nodes themselves. But in this case, if we want to, I want to kind of demonstrate the logic, and this is the simplest way to do it. So overall, we'll just assume it's true at the start. And if any of these recursive calls detect an imbalance, we'll set it to false. And then this function can just return that is AVL value. Now, one thing we have to fix up here, we want to reinsert these left heights and right heights. This is the same code we had in here before. Before it was just this code, and now we've placed in the variable name because we needed them here as well. And I do also need to make the center library copy. Let's run the code. Remember, all this is doing is starting at the root and recursively calculating heights. So it will return 0 at the null pointers, and then the leaves will get 0 for their two values here, and we'll combine them. We'll have a height of 1. From there, we'll move up the tree, up the recursive call chain, and calculate the heights of every single node. But as we're doing that, we check if the difference in heights is too great, and if it is, we essentially set this is AVL flag to false. And when we're done calculating and checking every single node, we can actually return this is AVL flag to get the overall quality of the tree. So let's submit. And it looks like we passed all the cases. So hopefully that helped. I think the main takeaway here is how to calculate these heights and how to check your balance factor. You will have to be a little bit more nuanced in your project, because you will have to check what rotation an imbalance will imply. And also, again, you want to be storing the height value in your nodes, just so you don't have to use anything like a global variable. But hopefully this did also help to show you how you can implement recursive procedures on a fundamental level to kind of traverse a tree like you might in Project 1. All right, if you have any questions, feel free to contact any TA on Slack, and good luck with your projects.